Einstein got his Nobel Prize for proving that cell phones don't cause cancer. Microwaves scare people because they're invisible, and scientists foolishly use the word radiation to describe the propagation of electromagnetic waves. 5G wireless is coming. It's going to be awesome. It's going to enable the Internet of Things and autonomous vehicles and all sorts of new technologies, unless unfounded fears about electrosmog derail the whole thing. I'm Professor Mark Hinders, Applied Science Department at William & Mary. I'm here today with Margaret Rooney. Margaret's a PhD student in applied science, and she's working on machine learning for cognitive radio and 5G wireless. So, Margaret, maybe you could tell us a little bit about what 5G is?
Sure. So, over the last several years, the number of devices that require access to the electromagnetic spectrum has increased rather dramatically. So this includes things like phones, laptops, tablets, wearables, and even smart appliances. But even though the number of devices has increased, the area of the spectrum that's allotted to support these devices hasn't expanded. So companies have looked into developing 5G wireless networks, which will use millimeter wave bands ranging from 3 gigahertz to 300 gigahertz. And this lightly licensed area of the spectrum will allow for much higher data transfer rates and will support the growing number of devices.
Okay, cool. So maybe I should explain first about the electromagnetic spectrum?
Yes.
Okay, so you know there's different colors of light, RGB, right? Okay, that's the things that you can see. But there are also colors of light you can't see. On the other side of violet is what's formerly called ultraviolet. My kids call that extra purple. On the other side of red is infrared. That's the heat radiation that you feel from a fireplace, for example. But there are other things in the other directions beyond ultraviolet. Remember, ultraviolet can give you skin cancer if you don't use sunscreen. There's also X-rays. That's on the other side of ultraviolet. And then beyond that is gamma rays. And that side of it, from the ultraviolet and shorter wavelengths, that's ionizing radiation. From the visible light down to the red and the infrared, that's non-ionizing radiation. And again, the word radiation scares people, but it's non-ionizing. It's perfectly safe. And so that's where cell phones and radios, and in the old days when they used to broadcast television and things like that, and millimeter wave, this unused band, this is in between where radios and Wi-Fi and things like that have been, and the red and the infrared light.
Right.
Okay? Good. Okay, so that's the electromagnetic spectrum. So where is 5G again?
So 5G is between the 3 gigahertz and 300 gigahertz area of the spectrum. So the current mobile communications channel is only between 300 megahertz and 3 gigahertz, so these frequencies will be substantially higher.
Okay, so maybe you could tell us a little bit about this thing, which is just sitting right there.
So this is a universal software radio peripheral. It's a software-defined radio. So what that means is it uses a laptop or some other sort of connected computer to transmit signals, and you can adapt all the transmission parameters. So you can change the modulation, the amplitude, and the frequencies that are being transmitted on it.
Okay, so when we're at higher frequencies, shorter wavelengths, one of the things that's going to happen is objects in the environment are going to affect electromagnetic propagation. So, for example, at these higher frequencies, millimeter waves, if our friends show up with their truck in order to empty the trash, that can block the signal. That isn't going to be an issue for cell phones now, but the 5G, the millimeter waves, those sorts of things can be a serious issue. And so we've got several of these software-defined radios, right?
Right, yeah.
Okay, so what are we doing with those?
So we're using these to transmit signals in various indoor and outdoor locations, just to study how the transmitted signals are being impacted by the built environment. So how the signals themselves are interacting with, say, buildings, trees, trucks,
white pickup trucks, yeah.
Exactly.
And so this reminds me of the old days. During the first Gulf War, I was a captain in the Air Force. I have no skills that are useful in wartime, but they gave me a medal for writing equations on the chalkboard during the first Gulf War. Maxwell's equations, and we were writing the equations to understand how radar interacted with things. One aspect of that is to try to make things hard to detect on radar. The other side of it is trying to detect things that are hard to detect on radar. So it's kind of fun for me to get back into this thing that I was doing so many years ago, to write the equations, the scattering equations, do simulations to understand how radio waves are going to interact with trucks and buildings and trees. So you've been out and about with your
Right.
software-defined radios. Tell us roughly what you've been doing.
So I've been transmitting signals between one USERP and another, and I've had them positioned in various different locations, inside in the lab, in populated areas inside the atrium of the building, and also outdoors, so on different sides of the building, transmitting between trees, around bushes, and just straight. Just to see whether I'm able to capture any, receive any data. Really.
Okay, so now let's talk about cognitive radio. This is another new thing. One of the things that's important about 5G is because it's much higher frequencies, the signal doesn't travel as far, so there's going to have to be a lot more cell towers, something on the order of a micro cell tower on every lamppost. And what that means is, depending on the built environment and who's using the spectrum, there's going to be lots of empty places where no one is transmitting, right?
Right.
So tell us a little bit about how this is going to work.
So, so the devices like a software-defined radio can sense the spectrum, and they can tell when a licensed user is transmitting information and when they're not. So by being able to detect these empty spaces by looking at, for example, control packets, which will tell you when radios are going to transmit and if they've already started transmitting information, the radios themselves can start transmitting information, and they'll stop as soon as the primary or the licensed user starts to transmit information.
So you can
again.
figure out who's who,
Right.
and who's supposed to be there, who's not supposed to be there.
Right.
Can you tell who's communicating with whom?
Right, yes, that's another thing that we're working on, by looking at the transmitted signals and making what we're calling wavelet fingerprints out of the signals.
Okay.
We're looking at sort of unique identifiers in the fingerprints to determine which devices themselves are communicating, just based on like hardware artifacts in the transmitted signals.
And those shapes we see in the fingerprints aren't detectable in the waveforms themselves. So this mathematical operation called the Wavelet Transform allows us to identify shapes in these fingerprint-like images that allow us to figure out who's who, who's talking to who.
Right.
Not what they're saying, that would be icky, but just keeping track of when it might be appropriate to have your phone or your Internet of Things device use the available spectrum because
Right.
nobody's using it and you don't want to waste it.
Mm-hmm. Yeah, and another great thing about the wavelet fingerprints is that, especially for these transmitted signals, the amplitude varies really drastically. So the fingerprints, they'll still retain the same sort of shapes and features even when the amplitude is changing dramatically.
So we think we can still detect the signal even if a truck pulls up behind us while
Right.
we're trying to talk. Is that
Right.
about it?
I think so.
All right, thank you very much. I'm Professor Mark Hinders, Department of Applied Science, College of William and Mary, as.wm.edu. Feel free to look us up on the web for more information about this project and other things we have going on in the lab. Spencer, lunch! Hot pocket.